So let's take a look at Gauss's lemma on polynomials, which says that if you start with two polynomials with integer coefficients that are primitive, then so is their product. So remember the definition of primitive. Primitive meant that the coefficients of your polynomial have greatest common divisor 1. So we'll prove this, but let's do an example just to clarify. The polynomials x squared plus 2x plus 3 and x squared plus 4 individually are primitive. This polynomial is primitive because the greatest common divisor of 1, 2, and 3 is 1, and the greatest common divisor of 1 and 4 is 1. So I have two primitive polynomials, and if you expand this, you get x to the fourth plus 2x cubed plus 7x squared plus 8x plus 12. And then if you look at the greatest common divisor of these coefficients, you also get 1. Okay, so let's prove it. I'm going to prove this by contradiction. So I'm going to suppose that my product FG is not primitive. That means there's some constant that divides every coefficient. That's not 1. A constant greater than 1 divides every coefficient. So I'm going to let P be a prime that divides every coefficient in FG. Okay, I'm going to define a ring homomorphism. So I'm going to define a ring homomorphism phi that takes polynomials with integer coefficients and gives you polynomials with coefficients in z mod p. And I'm going to do that by sending a polynomial, a n, x to the n, and so on, with integer coefficients to the polynomial with coefficients taken mod p, just by doing the straightforward evaluation of each coefficient taken mod p. So this would be a n mod p times x to the n, so on until I get to a0 mod p. So I just take each coefficient mod p. Now, technically, I guess I'd have to check that phi is indeed a ring homomorphism, but I'm going to leave that checking to you as an exercise. It's a more general fact that if I have any ring homomorphism from one ring to another, then it could be extended to be a ring homomorphism from polynomials in that ring to polynomials in the other, just by doing this same kind of operation. But nevertheless, it is an exercise that phi actually is a ring homomorphism. Okay, so then 0 is the evaluation of phi of f times g. The prime p divides every coefficient in fg. That means every coefficient is sent to 0 under this ring homomorphism. So I get the 0 polynomial when I apply this function phi to f times g. Now it's a ring homomorphism. That means this is phi of f times phi of g. Now, the ring z mod px, the ring of polynomials, is an integral domain. That's because z mod p is an integral domain. And I guess that's another exercise to prove that if you start with an integral domain and you look at polynomials with coefficients elements in your integral domain, then you still get an integral domain. So that's another exercise. If you start with an integral domain and create polynomials, then the polynomial ring is also an integral domain. So I'll ask you to verify that as well. But the definition of an integral domain is that when you have two terms that have product 0, one of the terms has to be 0. So either phi of f is 0 or phi of g is equal to 0. This means either every element in every coefficient in the polynomial f is divisible by p. So either every coefficient in f is divisible by p, or the same property is true for g. So every coefficient in g is divisible by p. I think that's the contradiction, lightning bolt. I don't think that it can be possible because we already said by hypothesis that f and g are primitive. That means the greatest common divisor of their coefficients is 1. There can be no prime p that divides every coefficient. So there, we're done. That's the end of the proof. That's Gauss's lemma, and we'll use it in our next video to prove an amazing result about reducible polynomials over the integers. Okay, I'll see you there.